All right, so let's continue with implementing the Croof language, which is a really simple proving math expressions. So last time we managed to finish the parser and we are able to parse expression from this language, right? I think that's pretty cool by itself. You know, it's a good tutorial of how to write a lexer and the parser. And for today, I was thinking to try and implement a really basic idea of trying to evaluate expressions. So we are gonna focus on implementing the eval keyword, let's say, and then maybe if we can actually do it with proof, that would be cool. But for now, let's see how we could implement eval. So what I was thinking is we'll skip type checking for now. Type checking would be cool, like making sure that plus is applied correctly here, even in these statements, which are like axioms, right? But we can skip that part for now. We'll try to not make type mistakes. But I'm not sure how types are gonna work, but we'll see. And what we can focus on is looking for these then symbols, and these expressions are the important ones. So I think it's called reflexive, like plus a plus b is equal to b plus a. That's one formula that we have here, like one definition. Another one is a plus 0 is equal to a, and the last one is f of 0 is equal to 1. Maybe we can even say here f of 0 plus 0. Now let's rerun this thing. Where is the eval? Okay, I think it's higher up. Okay, it's here. Right, so we have this function f called on number 0, operator plus, and number 0. And we are gonna assume that, you know, types are correct. So we are not gonna worry about typing for now. We might in the future. So my idea for how we can evaluate this thing is, well, usually in math, when when you get stuck and you only know some formulas, you might just try to do something which I guess I can call it backtracking. Like you can try all the formulas, get to a certain point, then you're like, okay, this seems promising, let's try all the formulas I know on this thing, and then you go next, and so on. So it's something like a depth, well, you know, I wouldn't say it's depth first search, because, well, it depends, right, on your approach. It can be like a breadth first search or a depth first search. You try all the formulas you know, so these three formulas on your expression, and you see how deep you can get, right? And you can already see maybe one problem. Let's say our algorithm will take this formula first, the first one, a plus b is equal to b plus a, and apply it on this thing. Let's just pretend we can write it down here, right? So we start with f plus 0, right? And then we apply this thing. So we are going to convert it into 0 plus f0, and then the algorithm will take this one again because it's the first one, right? So it's just gonna iterate through them, and it's gonna reach the same position as initially. So we might want to detect cycles, like it's useless to apply this thing twice because we get the same point. So we might want to do something like that, detecting the cycles. And then instead of, you know, applying this formula, maybe you want to try to apply the second one. And for the second one, we would get f of 0. And then, and what's interesting is that, well, we can see that it somehow matches, right? It has the same 0, so we are gonna have to figure out how can we tell that you can actually apply a formula, right? Because you cannot apply this thing. I mean, obviously you can apply it, but maybe some formulas don't make sense. Like for instance, f of 0, you cannot apply a plus b is equal to b plus a. It doesn't make sense. But yeah, we'll have to see how we can actually tell that on a certain expression you can actually apply a formula. Like, what's the strategy to see that two expressions are the same or equivalent, I guess, right? And obviously, without any type checking and strict rules, it might be easier because we are just going to look at the AST, and if we take a look at operator addition, you can actually see that we have, well, I guess when I'm printing stuff, so let's zoom out a bit. When I do statement dump, for instance, where is the operator dump? For operator dump, I'm doing left hand side, operator right hand side, but you know, it's not really that big of a deal. It's like a tree structure, and in this thing you can actually have the plus, then you have a left hand side and the right hand side, right? And that thing is gonna be kind of similar to this formula. Like, we have a plus, we have a left hand side and the right hand side, so we might be able to just pattern match these things somehow. We'll see how. We'll try to do that. So yeah, let's go into main.c and let's think about some kind of new data structure that we can call maybe inference or something, inference T, or interpreter. Maybe it's something like an interpreter or evaluator. Let's call it eval T maybe, although I think no, yeah, it's fine. Or solver, I guess, or maybe even we can call it Croof. It's the Croof. You know, that this would be the highlight of the series, when Croof actually croofed itself. That's maybe, but no, let's call it solver. Let's call it solver and not be that insane about it. So solver, I'm not sure what fields it's gonna have, but I guess we want to contain some kind of state for the solver. Not sure yet what we want here, but maybe we'll do want a structure. Okay, and obviously we need, same way we parse the program here, we want to solve a program. So let's have a function that maybe looks similar to program dump. Solver solve program, or I guess solver solve. Again, I'm not sure what solver is gonna need, not quite sure, but yeah, it's fine. Okay, another thing we missed here maybe is we should keep track of the evals. So evals are just gonna be expression t's, and you know, we just need the evaluations. It's not that complicated. We just need to go here, and instead of just printing the eval, we are going to store it. So we need to do something like this. So we create an expression, we parse it, and we need to append it. So I'm just gonna append that evaluation inside of evals. And let's not forget about initializing the expression t evals. Okay, nice. So just initialize the structure. Okay, maybe we don't need to do that here. Maybe we can just, instead of program dump, well, why not? Let's just do another for loop just for now. just to see it better. So we are gonna have expression t eval. We need to take this thing into eval from evals. Okay, and then we need to expression dump. Okay, and maybe the other thing would be the proofs, but for now I would actually just comment them out because I don't care about the proofs right now, so we don't even want to see them at this point. So let's rerun this thing. We should see the evaluation here. So the point would be to just try to solve this thing now. Okay, so this one is going to take in the solver. Again, I'm not sure if we are going to need something in the solver. We'll see. But what we need actually is to iterate the evaluations. So maybe it's going to be solve program. Solve program, and I would say that maybe the obvious thing is to just start with the basics, which is creating a for loop over the evaluations, taking an evaluation, and now we have an eval. What I'm thinking at this point is if we want to have something like maybe solve evaluation, then ds dynamic array statements statement t, and maybe an expression t pointer eval. So maybe what's interesting about this one is if we solve an expression, we also want to have an output for that expression, right? And I would say that's pretty important, that we might want an output. I mean, obviously, you know, this is like const, you wouldn't want to change it. But even then, maybe we just want to print them, like print the answers for now, I guess. Let's just print the answers for now. Let's not return the answers. Not sure yet how to, like, what to use the answer for outside of this function. So let's just print the answer. Okay, so we have all the statements and a single expression. Right. So one idea for what the solver would have as a field is maybe some kind of mapping between an AST and some kind of result. But the problem is if we do that, I mean, a visited list would still work, like a set with all the visited positions. The only problem is like that would make it a bit more efficient because you can reuse for other evaluations as well. but maybe I just want to have a like a separate DFS function. Okay, so let's think about it. So we might want to have some kind of dynamic array visited, maybe, and this could be just expression t's. Okay, and we have to initialize it. So dynamic array init size of expression t. Solver solve eval solver program statements and eval. Maybe we want to make this thing int just to be able to have some kind of int result. Return default one. Right, and we can make this one return int as well. Yes, dynamic array free. Pass visited in here and return result. Okay, perfect. So I think that double check expression. I think that the expression should be invisited. So dynamic array append, inside of visited we want to put eval. Not sure yet though. Let's do another function for solver solve DFS, or maybe I don't know, this is gonna be a static one anyways. Obviously it's gonna need all of these arguments. So let's think about it. Obviously it's gonna need solver, maybe all the statements to know what to choose. Like this is the state, which could be part of the solver, but yeah, who cares? Eval is the expression that we are trying to solve. Obviously another thing that we will need is dynamic array visited, and we need it as a reference because we want to be able to change it. This is going to contain expression t's, right? And do we need anything else? Not sure, honestly, not sure. So I would say that the first thing we need to do is a for loop over the statements. So let's unsigned I, 0, I is less than statements dot count I plus plus, and I could have just copy pasted this thing, which is the same stuff. Okay, so we just read from the statements, and now I would like we are gonna ignore the defines, right? Although at this point we should be able to ignore the defines because type checking should happen before, or maybe we can type check directly here, like Note, we ignore the types for now. Right? But what's more interesting, if we look at the statement, is it has an equality. And the equality has two expressions. I think that for now we are also ignoring going from left to right. No, from right to left. We are just going to use these as something like, if we find a equal to b, then we are gonna replace it with b plus a, right? So it's not really equivalence for now. It's more like, if we find this thing, we replace it with this. And then maybe we can add a rule that says that if a is equal to b, then b is equal to a, or something. It's, yeah. And maybe that's gonna help here. So we have this equality, right? And we need this left hand side, but this is also pointer. I think I want to add, so solver program, this should be a const. We don't want to change it. This needs to be a const. What? Get ref? I mean, that's pretty stupid though. Get ref should be const. Okay. That's weird. Because it doesn't change it. Anyway, doesn't matter. But yeah, like here it should be const. We don't change this evaluation. We don't really change this thing, but it's not a pointer. Okay, here this this thing, we don't change it. I mean, let's keep it as it was. I don't really care about consts, but I mean, you get the point. We are not gonna change them anyways. So we have this left hand side as an expression, and we also have eval as an expression. So we might need some kind of function if something here is going to be a function, something is true, let's say. We are going to need to do something about this. Maybe we can think about a name for this function. It's something like similar to type inference, right? Where we are taking two objects and check if they are compatible. Is compatible. Right, I'm not sure. Static boolean is compatible, and we need expression t, expression 1, and expression t pointer expression 2. Maybe that's, and let's say it's false for now. You do implement. Okay, obviously, yeah, sure, whatever. So this checks if two expressions are compatible, which, I mean, basically we are gonna look at the AST and we are gonna check if we have the same operator. That's more important. And yeah, I mean, it feels kind of similar to what we did with the stack language when we were checking, when we were doing type checking, but we'll see. Like here we are only checking if they look similar, and we are also interested in the fact that this formula, so the maybe it needs a different name. So maybe it's something like axiom and expression, and it's more like a is subset, but yeah, I feel it like is compatible. So we want to look at a plus b and f of 0 plus 0, and we need to say, okay, b is a variable, 0 is a number, so it is a subset, right? 0 is a subset of b, so because b is like any m. Okay, but if we had here like a plus 1, both are symbols and they are not equal, so they are not compatible. That's my idea. And here, for instance, you can see that we have a plus 0, and here we have something plus 0, and the zeros are equal, even though they are symbols, so we can pattern match this thing, so it is compatible. Again, not extremely convinced about the name of this function, but maybe we can imagine a better name. Okay, so if they are compatible though, we need to subtract, we need to pattern match. What was subster? I'm thinking about the name from the make file, like when you substitute, that's the word I was thinking about. I guess substitute makes sense. So we want to basically maybe but how are we gonna do substitute? I'm not sure. To do substitute or whatever, right? And that's compatible. We do a substitute, and we might create a new expression because otherwise doesn't make sense. So expression t it's like eval prime, so maybe we can just call it eval1 is going to be equal to something, right? I think we need to check if eval1 is invisited. So static boolean is visited, and let's do here this dynamic array pointer visited and expression the pointer expression to do implement return false. So we need to do something like if is visited, I said visited and eval1. So if these are visited, then we don't do anything, but if it's not visited, then we need to do solve dfs. Solver is the first argument, statements still goes. Here we pass eval1 and visited. And I mean, if this thing is not equal to 0, then we just return defer1. Maybe it was an error with allocations or something. Defer return result. Okay, and I think the other solver. Okay, and I think the other thing obviously we need to do is add eval in visited. Maybe we add it here. So that's basically the function. We need to copy paste. Let's add it, and let's say this is unreachable, like it cannot fail, and we just add that to visited. Nice. Now a good question would be, how do we backtrack? Like, how do we know what we did? Not exactly sure, but let's dump expression eval. Let's just see the expression for now. Each time we go into this thing, we're gonna take a look at the description, or I guess expression. Okay, and now we have to implement the compatible function and substitution. That's interesting. And here we need to call the DFS. So solver solve DFS. Let's pass the solver, let's pass the statements, the eval expression, and visited. Obviously, if this thing, then we just return defer or 1. Okay, I mean, I see that we don't really use solver, so maybe we'll delete it. I don't know. So how does is compatible work? Let's think about it. So we have two expressions. Well, first of all, we need them to be exactly equal at some extent. All right, so what kind of expressions do we have here? Well, we have the kind, that's important. So let's grab all of this stuff. Okay, so we have set, which is basically something like this. I'm not sure what we can use set for. Again, not exactly sure. Okay, the other important thing is equality can be null. So if statement equality is equal to null, then we just continue. We don't care about expressions that don't have an equality. Let's just get that out of the way. Anyway, so for set expressions, I'm not sure what it can be useful for, so I'm just gonna ignore it. Name would be the name of a set. Again, not sure about that either. Number is an interesting one, function as well, operator as well, and parentheses as well. So these are the only important ones, I would say, at least for now. So if axiom kind is equal to expression kind parent, let's start with the parentheses, right? Because the parentheses is just gonna be a recursive call, I would assume. And expression kind is also expression parentheses. Then we just return is compatible of axiom parent and expression parent. I think we need to reference them. Oh, it's parent, and inside of parent we have expression. Okay. So it was fine. I need to say dot expr. So we just recursively call to the inside of the parentheses. Okay, nice. Then the other option, which I said it's interesting, is if both of them are operators. So if we have expression kind operator and expression kind is expression kind operator, that's the interesting one. Well, in this case, we have maybe a boolean is same operator, whatever, is gonna be axiom operator dot value. So value is basically the string slice, and we have a function ds string slice equals, and this function checks if two string slices are equal. So we can just pass expression operator value, and this is going to return us a boolean. It's going to tell us if these two operators are the same. And why is that important? Well, operators are basically symbols. So if you have here a minus, then you cannot apply. It's not compatible right out of the start because it's not the same operator. You cannot apply that formula. Different operators, different functions. So you cannot apply it. So we need it to be the same operator. Maybe we don't, maybe it's just an if. Maybe it's the continuation of this. So it's like this. All right. I mean, that makes it kind of long, so I'm just gonna do it like this. Okay. So we have the same operator on both expressions. So now we have to check if the left-hand side is compatible with the left-hand side of the other one, and the right-hand side is compatible with the right-hand side of the other one. So I'm just gonna do return. Well, honestly, just to make it a bit shorter here, I'm just gonna do this. So it's the same thing. And what is compatible axiom operator dot left hand side, and this is an expression with expression operator left hand side, and is compatible axiom operator right hand side and expression operator right hand side. So we need these to be compatible with each other. That's pretty cool. Okay, so we got these two. The next one is function. So the next one is function and number. Okay. So I would say that if now it's interesting because it's two different kind of cases. You can see it actually here and here. A and f of 0 are both functions, right? Like that's by our definition. They are both functions. On one hand, A is defined as for all A, blah, blah, A, right? But in this case, f is called with like an argument. So I would argue that we have two kind of cases. When we have a simple variable, right? And when we have a function call. And when we have a simple variable, you can basically have anything on the expression because it doesn't matter. But if you have a function call, then it needs to be matching. Like the function name needs to be matching. That's the first case. And then the arguments need to be compatible. So the arguments of the function need to be compatible. Okay, makes sense? I think so. Hopefully it makes sense for you too. Because again, if you have a function call, it's important to have the same name of the function because it's the same thing as the operator. Right? I was thinking, can you have maybe different function names but they refer to the same function? Not sure. I think it's just the case of the operators. Yeah, I think a function call is the same thing as an operator. Yeah, I guess it makes sense. So let's do it like that then. Okay, so if we have a function with arguments, then we treat it the same as the operator. But if it's a function with no arguments, meaning a variable, then we treat it differently, like a variable. But even then, if you have something like f, so if you would have a rule like f of a plus 0 is equal to, I don't know, some, it doesn't matter, f of a, and then you want to prove that a plus 0 is equal to a, this also works because f of a actually returns an m. So that's gonna be a bit rough. Or even 1 plus 0. And this thing also is compatible with 1. Or I should say 1 is compatible with f of a. Because f of a returns m. But since we don't have type checking, that's a bit tricky. Like, type checking would be needed here because we want to know the type of this thing. I would say the type of this thing is important here, isn't it? Okay, let's just say since we don't have type checking for now, that if both of them are variables, if yeah, let's just say that if both of them are variables, then it's automatically compatible. Let's just pretend that it's that way. But as I said, if you have a function, then you need to check the types. It's more tricky than just this, but if both of them are variables, it's compatible out of the box. Okay, so if axiom kind is expression kind name, and expression kind is also expression kind name, then we just return true. But as a small note, maybe here we need to check that the types are matching. So the types of those functions, right? Oh, I mean here it's function, not name, but function. So function. All right. And the last option is if the axiom is a function, expression kind function, and expression kind is expression kind number. Here we just return true, but again, note we still need to check types, because maybe this function returns something and the number is not in that set, so then it's not compatible. But for now we can just pretend. And for the last, did I say that was no, this is the last case. Axiom kind is equal to expression kind number, and expression kind is also number. Then we need them to be the same. So this string slice equals axiom number dot value, which is a string slice, is equal to expr number value, and otherwise any other case it's false, right? So that's when we can pattern match, basically. Okay, fair enough. So this would be is compatible. Now what I'm not sure is something that I don't like is we need to call substitute, and basically what substitute is gonna do the same thing again. That's kind of ugly, not gonna lie. So can I somehow combine these two? Oh no. Anyway, whatever. Let's implement visited for now. So to implement visited, we need a for loop unsigned. And now, we could have used the set here. I don't have a set implemented, so I'm not gonna worry about it. But we have count I plus plus, and the visited array is an array of expressions. That's good. Oops, oh my god. wait, what? So instead of visited, we don't need that. We have, let's call it item because it comes from the array. We need to check if expressions are equal. That's cool. If expression equal expert and item, then we return true, otherwise return false. So expression dump. Let's implement the expression equal function. Expression equal function then let's do it here. So expression equal is going to be expression 1 and expression t pointer expert 2, and the header is compatible, which is kind of similar, honestly. It's just that we have expression 1, right? If both of them are equal, we need to recursively call this thing, and it's boolean. Well, it's really similar though. That's cool. I should have renamed them. Well, it is what it is. So if they are equal, expression 1 with expression 2 and expression 1 with expression 2, that's perfect. If we have functions, now this one is interesting, we need them. We need to make sure that everything is equal here. So expression 1 name value, so this is for the name. Wait, what? Oh no, it's a function dot value is the name of the function and args is the arguments. So is same is going to be this string slice equals, and we pass in this thing and expression 2 function value, it's a reference, and then we need a for loop. For int I is equal to 0, I is less than boolean is same length function, where we are interested in expression 1 function args dot count to be equal to expression 2 function args count. Let's do expression 1 function args count I plus plus if is if not is same function. Wait, let's use the Morgan here. So normally I would say if same function or is same len, then we just return false, right? Because it's false, obviously. But this would change into AND. So, wait, it's an OR here. So if it's not the same function or it's not the same length, we return false. Otherwise, we do this for loop. And if I need this thing, I need this. So we have argument I, right? We take it argument 1i and argument 2i. And here we have expression 1 function dot args, and we read argument 1. Then we read argument 2. And if not expression equals arg1i and arg2i, we can just return false. Otherwise, at the end of this thing, we return true. Right? It means that the function calls were equal. So we have the parentheses, parentheses operator function. We have next number. The fuck is this? We have a number, so expression 1 and expression 2. This one is pretty obvious. Numbers need to be equal. The next one is name, and you guessed it, the names need to be equal. Now, yeah, sure, like expression equal, it's not really the same as expression equivalent, let's say. Like two expressions are equivalent. But here we need, we could use equivalence, but who cares? It's way too hard to do that, so we are just gonna keep it with equal. Okay, and the last one is the set. So we are interested in seeing if these two are sets. So if it's a set, both of them, we need to see if it's the same length. I think it's values what? Items. So if not is same len, you just return false. Right? Otherwise we have to do something like this. Do an iteration over set items count. Oops, over set items, and I guess I want to rename this thing into like item. And then we check if they are equal, and then return true, otherwise return false. So this should help with checking if two expressions are exactly equal, like not even looking at equivalence or something, it's just plain equal. Maybe we want to implement something like equivalence instead. would be more efficient, let's say. Okay, whatever. So we also check that. Again, as I said, maybe compatible should also try to apply the substitution. Because is compatible is basically just checking, but it's not also replacing the thing. So I have to implement this thing twice, which is kind of annoying if you think about it. And that's why I say here, I'm not sure if I want to have a try substitute instead. Maybe let's do try substitute. It's gonna make it much easier. Try subs whatever, let's copy paste try substitute and eval1, right, with the reference. And I think instead I want this thing to be equal to 0, like dsok, basically dsok, you know. But I'm just gonna keep it 0. So it's gonna try to substitute into eval and write that to eval1. Makes sense. And if it's not visited, then it checks solve DFS. Okay, I think that makes sense. I was like, maybe I can even do it like this just to save on space. Okay, so let's do try substitute instead of this thing. Try substitute. So here we have expression t pointer subst, and let's pass subst in. Oh, now that's interesting. When I substitute the expression, for instance here with parentheses, I need some stuff. So what I need to do is subst kind is equal to expression kind parentheses, and then subst parent, right, is this thing, dot expression. Now the funny thing is expression is a pointer, so we need to allocate it, ds malloc null and size of expression t, right, and I think we need to pass in the parent expression. Okay, so then we have an operator try substitute. Here we need to pass in subst operator left hand side, and this is also pointer, so we need to allocate it. Subst left hand side, and obviously we need to set the kind as well. Expression operator. And maybe the other thing we need to set, subst operator value is expression operator value. Oh god, such a huge sneeze, Jesus. So I guess we're gonna say the operator and then a right hand side. Okay, so subst operator right hand side. Okay, so if we have a function and function, we need to do something about it, which I think is just replace it with the axiom function. I think that's all we have to do. Am I right? Oh no, I'm dumb. Here I need to use equivalence, equality. So instead of axiom, we'll say equality and left hand side. Yeah. Whoa. The fuck? Wait, was it a pointer before? Ah, it needs an equality. Shit. Oh no, let's keep it. Fuck. Oh god damn. This is kind of cooked though. Because we want to replace it with A, but we need a mapping from, yeah. So do we even need this? I think it was fine with is compatible, but I think we needed to return the mapping. That's what I think we needed to do actually. I think we needed to return the mapping. So is compatible. I think it was fine. We just needed to return a mapping. So in here, ds dynamic array, the mapping, and let's say this is a mapping. I'm not sure what the type is gonna be, but here we pass in the mapping as it is, mapping as well, mapping, and we are just gonna ignore most of the stuff. So if we have two functions, we want to add a mapping from expression to axiom. So it's going to be expression arrow function. Yeah, I guess it's going to be from expression to axiom itself. So like we are gonna replace expression with that. What? Okay, 1 second. So if I'm looking at f0 plus 0 and we have a plus 0, let's say, and I create a mapping that looks like f0 goes to A, and I don't really care about, but we know that this thing is equal to A though, that's the important part. So they are compatible, so I have this thing and this thing, and I know that A goes to f of 0, so we replace it with the right hand side, and in the right hand side we have to replace A with f of 0. Okay, makes sense. So basically in this mapping, let's create a type def struct key. I guess it's gonna be kv substitution kv, or I guess it's gonna be subst kv. I don't want to type that much every time. Subst kv, and we need as I said here, the like two expressions. One is gonna be from the expression, and one is gonna be from the axiom. Okay, so we are gonna have expression t pointer, I guess, key, and expression t pointer value. So here is gonna be subst kv, yeah, whatever. All right, so the key is gonna be this expression, and the value is gonna be the axiom, right? Yeah, I know that it matters that much. So let's do subst kv is literal of subst kv, and in here I think I'm gonna pass the axiom and expression like this to get the key and the value. Okay, so let me just dynamic array append. Where is append? The fuck is append? Wait, I used an append. What the fuck? Oh, it's here. Yeah, anyway, so let's try to append into the mapping the key value. So kv. One thing maybe we forgot. No, it's fine. So at this point we need to add this mapping. Okay, and if we have expression function and number, now this one is interesting. If we have function and number, like let's say this one, oops, let's say we have this expression and a plus 0, so a maps to a, that's whatever, and then b with 0. I mean, it's the same thing, right? We have to do the same thing. We just have to map the b into a 0. So yeah, that's pretty straightforward as well. And when we have a number with a number, we don't care. If the number is gonna stay a number, they have to be equal. Okay, nice. So that's that. So let's try to get the mapping now. So here we need to pass in a mapping. So I'm just gonna define the mapping. I guess I'm gonna define it. It doesn't even matter. I'm gonna define it here. Yeah, I have to free it anyways. So yeah, it is what it is. Dynamic array init mapping size of subst kv. That's the first thing. Then we use it. and after we use it, we do substitute. We need the else case. Array 3. Thing is, I want to run substitute and then read instantly because it's gonna use a bunch of memory, I think. So here we need to substitute, and I'm gonna do statement equality, or I guess statement right hand side, equality right hand side, eval1, but it's gonna be a pointer, and mapping. So if this thing is not equal to 0, return defer 1, and we just exit. So substitute, how I think about it is we have the mapping with what we need to replace, right? So we need to replace b with a 0, or we need to replace a with f of 0, right? And then we just pass the right hand side and that mapping with each symbol to what needs to be replaced with, right? So we pass that thing, right? And the right hand side, and then eval1 is going to contain the result. Okay, so let's try to implement substitute. Static in substitute, we need to have expression, dynamic array, expression t pointer, basically axiom, let's still call it axiom. Yes, dynamic array mapping, and this is gonna be a subst kv, and expression t, like the evaluated expression, basically, right? That's the idea. So now we have to take a look at the axiom. Jesus, I think doing a switch should work. Switch axiom arrow kind. Oops. So if we have a set, do I just want to say that I don't know what to do for a set? Well, we have to do substitute for each thing. Yeah, I guess so. So let's take a look at the equal function. So expression equal. Where's the set one? But again, not sure what to do here. I would say we need to say the kind of the evaluation, or like the expression is expression kind set, right? Then eval set, we need to initialize the items, ds dynamic array init, size of, I think it's expressions. Really then? Yeah, it's expression. Okay. Then we need to pass through the axiom. Then we need the item. Axiom set. We take the item. We need to do break. And after we get the item, I think we need something like expression t item. Then we need to do substitute. I'm not even gonna worry about error handling, to be honest. Substitute. What do we have to pass in this thing? We have to pass item I, right? That's the like reference, the axiom thingy, the mapping, and item like this. And then dynamic array append into eval set items, the item. I guess that's fine. I think that's how the set should work. For the expression name, I'm not sure. I don't think we care that much. I think we care that much. Like, I would like to go through the mappings and find the mapping, if that's the case. Static I guess I'm just gonna call it static find mapping, and this is gonna take in the dynamic array of mappings. It's gonna take expression t pointer key and expression t pointer value, and it should be a boolean. Okay, we need this for loop. Oops. Find mapping. Mapping count, right? We go to mapping count. Mapping, we take subst kv, if expression equal kv key and key, then we are gonna return true, and we are gonna set value to kv value, but yeah, that's it. Whoa, I think it's fine. Dereference it like that. Okay, so find mapping, fair enough. So for name, for instance, we have to do find mapping. It needs the mapping. The key is basically the axiom, right? Let's think. The key, I think, yeah, is the axiom. So A turns to something. Okay, yeah. And the value, I think it's crazy, but I think it's eval. And obviously, if this thing doesn't work, shit. So So if this thing is true, then we return 0. You know the idea. But I'm just gonna do find mapping. For the number, pretty straightforward. So if the axiom kind is a number, then we just say eval is axiom, right? We don't have anything. Then if it's a function, I think we have to find mapping again. If it's an operator, now this one is interesting. If it's an operator, we need to set the type to operator. Eval operator left hand side. We need to shit, allocate them. Fuck, where they do allocation? Can't I allocate these things? Don't think so. No, I didn't. Okay, whatever. So if it's left hand side, then we need to ds malloc size of expression t. Right hand side, we also allocate it, and obviously the expression is operator. Right, so here we had set and we had to allocate and whatever. Here we had name, we just found the mapping. If it's a number, it's just a number. If it's a function, we also find the mapping. If it's an operator, we allocate left hand side and right hand side. And we need to substitute each one. So we need to say substitute axiom operator left hand side with mapping, and here we pass in eval operator left hand side, and here we do it for the right hand side operator right hand side. Okay, and if it's a parenthesis, we just need to set the type to kind parent. We have to allocate parent expression, boom, and we need to parent expr parent expr, and then return 0. Yeah, sure, we should probably do some error checking, but I think that's the main idea of substitute. Right, so substitute, then we visit again and we do all of that stuff. Okay, interesting. So this would be solve a DFS. Okay, we do a dump here at least. So let's go to main, and after program dump, let's do solver solve program. And honestly, since we don't need solver, it is what it is. We just saw that it's kind of pointless. Let's try to run this thing. So function 0 operator plus. We don't have some printing, right? Expression dump, printf. Let's do some double new lines. Let's put some equals like that just to have something. So I guess this is the first step where it tries, where it just prints it. Then see here it tried a plus b is equal to b plus a. That probably didn't work. So it resulted into numbers function f numbers. Holy shit. And then it got numbers number one. That's really cool actually. My only thing now at this point is, can we make it like just print the right path without, because here I assume actually kind of assume that it was a dead end. So let's do something like int dead end, right? So let's say it's a dead end, and if it gets into this thing, dead end becomes 1, so becomes 0. Okay, so dead end. And here if we had a dead end, if dead end printf dead end, I think that's how you are supposed to do that. Let's see. So here it got a dead end, you see. It didn't know what to do after it did the swap with a plus b is equal to b plus a. And then it got a dead end at number 1, but that's like expected because it's the solution. So now we have to figure out how can we tell that this is the solution, because we have two dead ends in our DFS, this one and then this one. But yeah, I mean, this is so cool that we actually have a solver, right? So it knows how to solve this thing. That's insanely cool. So yeah, I think this would be an interesting topic. How can we figure out which is the solution, right? Because someone can say, oh, this is the solution, like they're I don't know, they just wanted to see this as the solution. But someone can be, oh, but you know, I consider this one to be the solution. You know, it depends on each use case. So maybe show all of them, I don't know. Well, what I would consider a solution is the one that's the simplest form. Right? So if it's a number or a variable, but sometimes it can be multiple variables, so it's hard to say. But I think that what I consider a solution is the simplest one. So maybe we can look into the visited thingy and say something like just display the smallest one. But you know, just to be like as someone said, open source Wolfram Alpha, we would be really cool to show the steps, right? So I think a nice idea is to also store the steps you took. Maybe it's gonna be something similar to this KV. So we make use of the KV such that we can show the parents. So I mean, you know, that's pretty simple. You just keep a parents map. I usually do that in A star or like search algorithms. So maybe a mapping with parent in here, and yeah, we look for the smallest visited node at the end, and we consider that one to be the solution, right? And then we make use of the parent mapping such that we get the path that the algorithm took to get to the smallest expression. and somehow it looks ugly. Just kidding. Like, yeah, obviously, maybe we can have a way of printing them in the same way we read them, right? So that could also be a thing. But I wanted to showcase like the tokens. So yeah, maybe those are the next steps. Adding here, being able to build a path, and yeah, let's try to do that. Okay, so let's add the dynamic array for, usually I call it parent. So this is gonna be subst kv. I mean, it's more like an expression key value, but yeah. Okay. And I guess we need to pass it here, the parent mapping, right? So we don't need that end anymore. It was just for debug purposes. I guess even printing the expression is not gonna be needed. What we are going to need though is, once we go into visiting another node, subst kv, where did we use subst kv? When mapping, okay, I guess like this. We need to add a mapping from, so parent is gonna be, I guess, eval1 potentially, but since solve dfs, no, it's fine. So this should be parent. So the idea is we make a mapping from the node that we had as input to the node that we obtained. So although I think we want it the other way around, I think it's going to be easier the other way around, although it doesn't matter. So it is what it is. Okay, so we should have a find mapping, right? Makes sense. We have this function, even though it's not the most efficient thing ever, don't really care. Is compatible, should be fine, I don't see any problem. Is visited, it's like whatever. I wanted to add inside of substitute an if here. If this thing is not 0, we return, I guess we can just return 1 for now. Don't see an issue. Let me just int result is 0, so we do return before 1. Find mapping, this one returns a boolean, so if we find the mapping, then we return, no. If we don't find the mapping, we return before 1 because it was an error. We do that. If we don't find the mapping, we return before 1. And here, I guess, if this thing is not 0, we had an error. Return before 1. Just to make sure that we cover all the error cases, for 1, and here we return result and we add a differ thingy. Okay, nice. So then we appended the key value. Nice. And now we need to pass in here the parent. This dynamic array parent is 0, and this will have subst kv. Yeah, why not? So we are going to dynamic array init parent and size of subst kv. Okay, and here we pass parent. I guess instead of subst kv, I'm gonna rename it to expression per t, or I guess, I don't know, per t, and it is what it is. So we initialize it, we pass it in here, and now we have visited and parent. So I would like to have a function that finds the best expression, so, or I guess the smallest expression. So let's have something like static int smallest expression or something. Find smallest expression. It should take as an argument dynamic array expressions, and maybe expression t needs to be a pointer, right? Expression. We have int result is 0 if return result. So do we have anything else with find? Yeah, but not that one. This one is visited. This one is nice. So we need to go through all the expressions, right? We need to get one expression, and here we need to compare somehow. So how can we compare the expression to find the smallest one? Maybe just have something like a degree for an expression. So I don't know, something like static int expression degree, expression t pointer expression, and maybe I'm just gonna do a switch expression kind, right? And basically if it's a set, it's just return 0, it's one of the smallest ones. If it's just a name of a set, it's also 0. A number is also 0. Parenthesis is return 1 plus expression degree of expression arrow parent dot export. Right, so we recursively try. If it's an operator, it's actually should I say 1 plus? I guess so. So I'm gonna say 1 plus operator dot left hand side, and this is an expression, plus the same thing but for right hand side. I think I'm just gonna do 1 plus though. And if it's a function, I think I want to return 1. Just plain 1. Just plain 1. Maybe. I'm not sure right now. Maybe I have to look at the arguments as well. Not exactly sure. I mean, even for a set, you'd say that. So maybe also check the items. Note. Maybe also check the args. Not exactly sure, but I think that's a good way to do it. So let's have a int degree is max max int or something. Include stdint. Isn't something like max? See, max int. Oh, it's called int max from C limits. But do we really need it? Include the limits.h. Okay, it's inside of limits.h. Nice. Okay, whatever. Let's say we have int max, then we have a new degree is gonna be expression degree, and we pass it the item, and if new degree is better than I guess smaller than degree, we just star export is equal to star item, right? And at the end of everything we just return the result. Fair enough. Find smallest expression. So after all of this stuff we have to call something like find smallest expression. We pass in visited, and we also have to pass in the expression, which is basically the result. So I guess I'm just gonna do expression t, let's call it export, is 0 export, and expression dump export, maybe with a reference. The result is a new line, and if we run this thing again we get the result is number 1 for this evaluation, which is kind of cool if you'd ask me. Like, it knows to evaluate this thing and gets a 1, which is crazy. If I do plus f of 0 again, what would happen? I'm scared, honestly. The result is 0. Oh, mainly because I don't have any formulas. But if I do parentheses around this thing, it should get some result. Fuck, it doesn't. Well, did I mess anything up here? So here I need to show eval f. Not exactly sure if I messed anything up. So it finds this thing, but it doesn't know what to do with it. Well, yeah, it makes sense because sure, yeah, oof. Okay, I had too high expectations. Let's just leave it like this for now. I kind of understand what the problem is, but let's just keep it like this for now. Main issue is that inside of is how do I call it? Is compatible, right? If we have something, let's say, like a variable, so where is it? A function, and the function, we have that case. If we have a function and the number, we have the case. If we have a function and the parentheses, we don't have the case. So we also have to add the function and parentheses case. So function and kind of parent, right? So if the expression is a parenthesis, then it's still fine. We just have to map that thing into the parentheses, right? And it's reachable. So if we go to test, if I replace this thing with parentheses, it should now get a sigfold. Yeah. Well, let's. Well, I mean, if it's a parenthesis, I have to do something different though. I need to say expression parent dot export, right? And it still gets number one as the result because it evaluates something plus 0 is equal to something, right? And then inside of this something, it has that same formula again, so it gets number one, which is so cool. But what wouldn't work is this, because my algorithm doesn't know to look. I don't think it knows. Let's check. Yeah, it doesn't know how to look. Wait, what? Function 0 operator broken. Function 0 operator plus number 0. Something broken with the operator. Who knows what happened? Anyway, I guess it's gonna make it easier if we show the steps as well. So that's what we need to focus on. So we have the parent mapping, right? So let's have something like show path basically. So let's call it static int show path, and for the path we need the parent mapping, so this dynamic array parent and expression t, so this is pair t, expression t, basically the result, right? But I want it as a pointer and you'll see why. So what we need to do is find mapping, we give it a mapping which is parent, the result, and basically next. So let me just expression t next. Okay, 0, and we give it next. And I can say here something like while result is not equal to null, of course, we Although I like the recursive approach more, honestly. So I like it more if I do if result is equal to null, then we just return 0, for instance. Then otherwise we just find the mapping. We call show path of parent and next, right? And find mapping should return false at the end. But again, I don't care that it returns false. So shit, worst case. Actually, I do though. So if this thing, if not this thing, then we return 0. It means that we completed the thing. Otherwise, we call it recursively. Maybe I can do int result is equal to, but we don't care about. Yeah, I don't think I care about. I just want to return, then show path, and then we expression dump the result, I think. And then show path, parent, and expr. I think this should show printf the path is. I think this should show the path of the solution, right? Wait, what? The result is. Oh, the path is nothing. That's cool. Show path. So it's find mapping, show path, and then expression dump of result. So I mean, it should at least show the result, right? Or what? Maybe I put them in the wrong order. So I put eval1, which is the solution, and where I took the solution from. So if I try to find a mapping with result, I should find something. Let's do like a printf here. See if we actually get anything. Nope. The fuck? Printf %d parent.count. Fuck. 4 items. So yeah, it makes sense. 4 items in the path. Expression dump result. So in the result we should have number 1 exactly, but inside of the parent we don't have anything. Or that's weird. So for mapping parent count kv parent, and let's expression dump kv.key, for instance. kv.key. I'm curious to see the fuck. So is kv null? What? Wait. So parent, dynamic array append, and KV. F percentage P, new line. I mean, KV should have a value, like that's insane. It does have a value. How about, how about the key? It does also have a value. It's interesting. Oh, come on, man. So solver solve DFS. So the annoying part of using C, I guess. You know what I mean? Hmm. If I do here expression dump eval1, maybe a printf new line just to like that. So at least here it but what the fuck is this operator? Nothing here. It's weird. Function f. Wait, eval is, yeah, where it gets, and eval1 is like eval1 is where it gets, and that one. So we should have number 1 inside of this thing. I wonder why it's that broken. I mean, I give it reference to eval1, which is kind of stupid though. Shouldn't do that. Okay, let's actually do null for the first one, and then what I'm gonna do is kv key is ds malloc. I think we have to malloc size of expression t, forgive me, and then kv.key is equal to, or I guess ds mem copy kv.key from eval1 size of expression t. Okay, so yeah, you know, it was allocated on the stack. Okay, so printf, actually no, let's just remove that and just run it. The path is number 1. Okay, expression done, printf, let's printf new line there. So this has these values. So I would say that find mapping surely it has to find something like oh, but I'm printing the result. I should print next maybe. just to see what it is. The fuck? Expression dump key. Okay, what the fuck? And if I do something like in find mapping with this stuff, end result, printf percentage I percentage d \n. So 3, and it finds it. So I should, in fact, be able to do something like expression dump kv.value. Okay, what the fuck? Really? Oh, so do I? That's pretty cool. I need to kv.value malloc this as well. That's kind of annoying. Mem copy kv.value from a1 and size of expression t. Okay, apparently I had to allocate that as well. That's kind of stupid. Let me just print f a new line here. So the path is, we get to this thing, and then this thing. Yep, it kind of makes sense. Now I would like expression dump to actually change this kind of function and create a new one, maybe called expression print. Let's call it expression printf. So inside of here, maybe just replace dump with printf. And now I have to copy paste all of these. And just replace dump in here with printf, right? And thing is, we just print them as normal. So here, for instance, I don't add this extra name stuff. It's just that. Or for the number, I just print the number. For the function, just the function. Maybe just add commas like that. The operator, the parentheses, and that should be it. So expression dump show path, it's gonna use printf. Let's use printf. Okay, so the result is 1. The path is this. I would like to show the key as well, or something like that. So maybe with some kind of arrow, so going from something to something, you know what I mean? So here we printf the result, but I think I want to printf the next as well somehow. I don't know how though. Printf, maybe I need to do like an arrow here. Not exactly sure. It's the other way around, yeah. So the path is like this. You had this thing, it goes to this. Maybe I'm just gonna use arrow like this. So again, pretty cool, right? We start from this expression, it evaluates it to this. Maybe just saying which rule it uses could also be cool. Yeah. Then this one evaluates to that, and then f of 0 evaluates to 1, which, holy shit, that's pretty cool.